Hello everyone, welcome to my class. In today's class, I will cover the comparison test. So let me start the class right away. First quick note, so far we are discussing the series of positive terms. A positive series cannot oscillate, and if it diverges to infinite. To apply the comparison test, we need another familiar series to compare with, and our best friends are either geometric series, p-series, or harmonic series. So let me state the comparison test. The comparison test. Suppose series AN is a series with positive terms. If the series BN is another series with positive terms such that if Bn dominates An for all n and the bigger series Bn is convergent, then the smaller series An is convergent. 2. If An dominates Bn for all n and if the smaller series Bn is divergent, then the bigger series is divergent. Note, though the inequality in the comparison test is given for all n, we need to verify only it holds eventually. Alert! Suppose series AN and series BN are two series of positive terms and late series BN is known to be convergent. If An is greater than Bn for all n, then we cannot say anything about the series An. So that means if the smaller series converges, then we cannot say anything about the bigger series. Great. An improved version of the comparison test is the limit comparison test, which says two series behave in the same way if the limit of their ratio approaches a real number L. So let me state the limit comparison test here. Suppose given series AN and BN are two series with positive terms, and suppose the limit of their ratios AN or BN equals to L. That's the first case. For L between 0 and infinite, Bn is convergent, then An is convergent. 2. For L between 0 to infinite and if Bn is divergent, then series An is divergent. Great. So here we are focusing on our series and the denominator. Means if the Bn is convergent, then An is convergent. If Bn is divergent, then An is divergent for those value of L. Awesome. Quick note, a series converges if and only if a constant multiple of it converges. That's true. It allows us to keep only the highest power terms and ignore the rest. Great. So now let's do some worked examples. Example 1. Determine whether the series converges or diverges. So first part, so given series is 1 over 2 to the power n and then plus 1. So let's begin the solution. Let's take another series Bn equals to the series 1 over 2 to the n. We know this series 1 over 2 to the n being a geometric series converges. Then let's compare this two series here. Since 1 over 2n plus 1 is less than or equals to 1 over 2n, by comparison test, since the bigger series converges, so the smaller series converges. Awesome. Let's move on. 2. The given series is 1 over 2n minus 1. So let's begin the solution here. Note that we cannot use the comparison test as our geometric series 1 over 2n is less than or equals to 1 over 2n minus 1, and smaller series converges, it doesn't help us to conclude about the bigger series. So let's use limit comparison test. So here an is 1 over 2n minus 1, and let's say bn is 1 over 2n. Then let's look the limit of this ratio. Limit n goes to infinite, an over bn equals to limit n goes to infinite, an is 1 over 2n minus 1 divided by bn, which is 1 over 2n. Then you flip it, which is in the next step, and the limit n goes to infinite, 2 to the power n over 2 to the power n minus 1, it turns out to be 1. You write is corresponding functions and use underlying function test. Then you have to apply the L'Hopital's, then they cancel out here and it gives you 1. Okay, so hence, since we pick our series 1 over 2 to the n which converges, then by limit comparison test, the given series 1 over 2 to the power n minus 1 also converges. Great. Let's move on. This time let's do part C. So given series is 1 over radical n square plus 1. Summation runs from 1 to infinite. Let's see. So let's here. So 1 over radical n square plus 1 is less or equals to 1 over radical n square. When I take this positive number out, means I make a smaller denominator, so then this fraction is bigger, so which is same as 1 over n, and we know the series 1 over n is harmonic series which diverges, so that means the bigger diverges, it doesn't help us to conclude about the smaller series. That means comparison test is no help here. Then let's use a limit comparison test. So in limit comparison test, our an is 1 over radical n square plus 1, bn is 1 over n. Then let's look the limit of this ratio, an over bn. So in the next step, copy the limit as it is. An is 1 over radical n square plus 1 over bn is 1 over n. This n you flip it, and in the next step we can factor the n outside, so then we have limit n goes to infinite, n in the numerator as it is, in the denominator factor n out, then here under the radical 1 plus n square left. Then take the limit, then this fraction goes to 0, cancel this n, so then it gives us 1, which is a positive number. So hence, since we pick the series, the harmonic series which is diverges, then by limit comparison test the given series also diverges. Awesome. Now let's move on. This time let's do part D. The given series is natural log of n over n. Summation runs from 1 to infinite. So let's begin the solutions. Here an equals to ln n over n, which is obviously greater than or equals to 1 over n for n greater than e, because ln e is 1, and if you put n bigger than e, this is bigger than 1, I put the same denominator, so I have a comparison here. And we know the smaller series diverges, being a harmonic series, then by comparison test, obviously the bigger series diverges. So short and sweet. Great. So let's move on. Let's do this another type here. Part E, so given series is 7n over 2 times cube root of 5 plus n to the power 5, summation runs from 1 to infinite. Let's begin the solutions. Here's a quick idea. Here under the radical here, 5 plus n to the power 5 is approximately n to the power 5, the dominant part of the denominator. Then we can rewrite our nth term, an equals to 7n over 2 times cube root of 5 plus n to the power 5, approximately 7n over, let's take this 5 out, 2 times cube root of n to the power 5. Okay, and this equals to, let's separate the constant, so pull the constant outside, then we have n over n power 5 third. This equals to 7/2 constant as it is. Then bring this n also down in the denominator by switching the sign. So then we have n to the power 5 third minus 1, which is n to the power 2 third, and we know this series 7 over 2 summations 1 over n power 2 third is being a p series. P is equals to 2 third less than 1 diverges. So take Bn equals to, now the series of Bn is the series of this one, 1 over n power 2 third, so Bn equals to 1 over n power 2 third. We already mentioned this series diverges. Then by limit comparison test, let's take the limit of the ratio. Limit n goes to infinite, an over bn equals to limit n goes to infinite. What's my an? An is here, 7n over 2 times cube root of 5 plus n to the power 5 over bn is 1 over n to the power 2 third. The next step, limit copy as it is, then 7/2 the constant pull outside, and we need to flip this one. So this n 2 third goes on the numerator and add to the n, which becomes n to the power 5 third over, same as this one, cube root of 5 plus n to the power 5. And then from here, when you simplify put this limit inside, so then this turns out to be 1. That means I have only 7/2, which is positive, since the series is divergent, because we already talked here being p series. By limit convergence test, the given series diverges. Great. So now let's move on. Let's do another example, part F. Let's check whether this series is convergent or divergent. The given series is 1 over n factorial, n equals to 1 to infinite. Note, n factorial is, we know, n times n minus 1 times n minus 2 dot 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 times 3 times 2 times 1, and we know 0 factorial is 1, right? So this is n factorial. Then let's make a small trick here. We are trying to find some sort of inequality. So let's keep this 1 as it is, then replace all of these numbers by 2. So replace n by 2, replace n minus 1 by 2 dot dot dot, replace 3 by 2 and 2 itself. That means we are replacing these numbers by a smaller number. So that means this expression is obviously less than or equals to. I hope this makes sense to you all. And we replace n many terms, right? Keeping 1 as it is, then I'm replacing from 2 to n, means total n minus 1 terms. So that means my 2, how many 2's there? N minus 1. So 2 power n minus 1. Then this 1 over n factorials, I can bound above by 1 over 2 to the power n minus 1. And this series, we know this series is convergent, right? Since this series, the series on the right hand side is convergent, being a geometric series with common ratio is 1/2, which is less than 1. Hence by comparison test, the given series of 1 over n factorial also converges. Great. So here's I worked out in details, but as an aside, we know this one also. We know n square is less than n factorial for n greater than or equals to 4. So that means we can bound 1 over n factorials from above by 1 over n square, and we know 1 over n square being a p series converges, so smaller converges. And same as here also. Okay, so let's move on. This time let's do example G. This is very important type series here. So let's do number G. Let's see whether this series is convergent or divergent. The given series is n factorial over n to the power n. Summation runs from 1 to infinite. Let's begin the solutions. Here, nth term is an equals to n factorial over n to the power n, which you can rewrite as n factorial is n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1, and we know 0 factorial is 1. And in the denominator, n to the power n means n many n. N dot 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 n. So now, to find the inequality, let's use small trick here. The trick is replace all the numbers up to 3 by n. So n as it is, replace n minus 1 by n, dot dot dot, replace 3 by n, 2 1 as it is. So that means I'm replacing in my numerators from n to 3 by the bigger number, which is n. So obviously this inequality is 2. Copy the denominator. Then we can cancel these n's. So what left? 2 over n, 1 over n left. So that means we have 2 over n square left. And this part is, I'm looking for some sort of series to compare. Now I found the p series. The p series, which is bigger than this given series. P series convergent means the given series also convergent. That's the idea. Since the series of 2 over n square being a p series, where p equals to 2 greater than 1 is convergent, then by comparison test, the given series is convergent. Great. So we finish 2 other tests, comparison test and limit comparison test, in today's class. Thank you.